we're going to start with 2017, number 1. We're given a table, and it says a tank has a height of 10 feet. The area of a horizontal cross-section of the tank at height h is given by the function a, where a of h is measured in square feet. The function a is continuous and decreases as h increases. Selected values for a of h are given in the table above. For part A, use the left Riemann sum with 3 sub-intervals indicated by the data in the table to approximate the volume of the tank. Indicate units of measure. So this one we actually haven't talked about because it's in chapter 7 in our notes. So we haven't officially covered it, but we can still talk about it. I think it's good exposure talking about what the free response questions might be asking for or needing. Okay, so let's take a look at what this might look like. So for part A, to calculate a volume using cross sections, think of it as a deck of playing cards, right? So if we have a deck of cards, we've got all these 52 cards that are stacked up, right? And so if we looked at just one of the cards, right, this one single card, we could find the volume of it. Now, the volume would be the length times the width times the height, right? But it's so small that the volume is, or the depth is almost insignificant. This depth here is just the thinness of a piece of paper, right? So it's not going to necessarily be very much, right? But if we take all of those, each of these 52 cards, and start adding them together, then we can find the volume, okay? Find the volume of that deck of cards. And so if we one of the ways that we talk about adding up all these infinitely many things was an integral. Okay, so what we can do is we could use an integral of each of these cross sections. Okay, and that would tell me the volume. All right, so if I take the integral of all those areas, okay, so the integral of all the areas, the dx being the width, or the depth, the depth, and the areas would be length times width. And if you remember, an integral just means to add up. So if I add all the length times the width times the depth, then I'm going to get my volume. Okay, so that's what we're going to do in part A, is we're going to approximate these, I think, using a Riemann sum. Yep. All right, so let me get rid of this. And so what we'll have, the volume is going to equal, and it says, indicated by the table to approximate the volume of the tank. Well, the tank is measured from 0 to 10, so my integral will be from 0 to 10. And we're just going to add up all those cross sections which are given by a of h. Okay, and it says that each cross section of the tank is given by the function a. So these are the widths of each of, or the areas of each of my cross section. Okay, for the data in the table. So a left Riemann sum means we'll use the left endpoint of each of these subintervals. So between 0 and 2, the left endpoint would be 50.3. So this is going to be approximately equal to, the width we said was 2, and the height was 50.3. Plus the next one. The next one has a width of 3, and I would use the 15 or the 14.4. So plus 3 times 14.4 plus, and I think there's just one more, between 5 and 10 would be 5, and then a height of 6.5. Okay, and this is a calculator problem because it's one of the first ones on The free response from 2017, a graphing calculator is required for these questions. So we'll use our calculator on this one. So what we'll do is we will take 2 times 50.3 plus 3 times 14.4 plus 5 times 6.5 and get 176.3. And because this is volume, we're going to talk about cubic feet. Or if you put feet cubed, that'd be fine. All right, so that's part A. Now again, I know we necessarily haven't talked about this, but just talking about the problems, thinking about how AP may ask something, just kind of getting familiar with the format, I think will help benefit us, okay? And even then, like, part A is a good review of the left Riemann sum, and even here in part B, it's still going to be a good, it's going to help us, okay? So in part B, does the approximation in part A overestimate or underestimate the volume of a tank? Explain your reasoning. So in part B, because we're using a left Riemann sum, we're going to be using some rectangles. It says it's continuous and decreases. So if I have a continuous decreasing function, it's going to look something like this. And if I'm talking about a left endpoint, if I have a subinterval, I'm going to go up from the left-hand side to my function and make a rectangle. So we can see that that is going to be an overestimate. Now the picture isn't going to count for justification, so what we need to do is make sure that we are referencing the decreasing part. Okay, so the approximation in part A is an overestimate because A is decreasing. Okay? And we could say, and a left Riemann sum is used. All right? Okay, part C. Part C says the area in square feet of the horizontal cross-section at height h is modeled by the function f given by f of h. Based on this model, find the volume of the tank, indicate units of measure. Okay, so again, this is a similar idea as what we did in part A. It says the horizontal cross-section at height h is modeled by the function f. So if we take all these cross-sections and add them all up, we could find the volume. And the way we add up an infinite number of cross-sections is just using an integral. So what we're going to do in part C is just take the integral of f of h dh, and we're going to use we're going to use all the values of h that were given in the table, or not necessarily the values of h, but this interval from 0 to 10. Okay, so my integral is going to go from 0 to 10. And I'm going to use the function that's given in part C. So the integral from 0 to 10 of 50.3 over e to the 0.2 h plus h dh. Okay. Now, because I'm given a function, again, what I always like to do is put it as y1, just because I may be using it again in part D. I don't really know, but I know that chances are I may be needing it again. So I'm going to go ahead and put that into y1, just in case I need it again. So e raised to the 0.2x plus x. Now, on our calculators, we use x's, right? The h doesn't matter. Just as long as you're being consistent with the variable. Remember, to calculate an integral, you do math 9 from 0 to 10. This is going to be of y1, and it's dx. So 101.325. And this, the unit, since we're talking about volume, would be cubic, and H is measured in feet, so this would be in cubic feet. Okay. All right, part D. Water is pumped into the tank. When the height of the water is 5 feet, the height is increasing at a rate of 0.26 feet per minute. Using the model from part C, find the rate at which the volume of water is changing with respect to time when the height of the water is 5 feet. Okay, so in part D, we said that the volume was given by the integral from 0 to h of f of h dh. Okay, but what I want to do is I want to figure out the rate at which the volume of water is changing with respect to time. That's just a derivative, right? A rate is a derivative. So I want to take the derivative of this with respect to time. And I can't necessarily have h in the bounds and h in my function, so I'm going to change these to x. Okay, minor detail, but it could catch you, so make sure that whatever variable you use up here, you don't use down here. They have to be different. Okay, so when I take the derivative of this, we're going to take h and plug it in, so f of h, and then we're going to multiply. Because I'm taking the derivative with respect to time, I have to take the derivative of h with respect to time. I have to take the derivative of that bound. Okay, so this would be dh over dt. Okay. All right, so I want, let's see, it says when the height of the water is 5 feet. This is kind of like a related rates problem, but it's also connecting in some fundamental theorem of calculus because we're taking a derivative of an integral. All right, this is what they like, that multi-focus that I keep saying. This is a multi-focus problem. It's got some chain rule. You can kind of almost think of it as a related rate. Right? Chain rule and related rate almost kind of tie into each other. This is some fundamental theorem of calculus. There's a lot going on just this one problem, just this one part. Okay, so let's see. It says when the height of the water is at 5 feet. So the change of the volume at 5 feet, we're going to plug in 5 for h. So f of 5, and then dh dt at h equals 5. And I think it gives us what the change of height with respect to time at h equals 5. And it says the height is increasing at the rate of 0.26 foot per minute. So that dh dt is just 0.26. Okay. Now the f of 5, that f function is what we put in as y1. Okay. So if I want to find f of 5, I could just go alpha trace y1 of 5. 6.5129. I'll take that times 0.26. Whoops. And get 1.694. But what are my units? Right? So the units on this one, because we're talking about volume, it would be feet cubed. And the time in this problem is all measured in minutes. Okay, so the answer here would be 1.694 cubic feet per minute. All right, let's talk about some points on this one. Where would they give you the points? Right off the bat, as long as you have the correct units in part A, C, and D, so the units in A, C, and D, that would get you 1 point. All right. For part A, you'd have 1 point for setting up your left Riemann sum and then 1 point for your approximation. In part B, it's just 1 point for your answer and your justification, or saying that it's an overestimate with your reason. In part C, you'd have 1 point for your integral and 1 point for your answer. And then in part D, it would be 3 points. It would be 2 points for this, which would be all or nothing, and then 1 point for your answer. Okay? Again, I don't think this one's going to come up because they actually told us that this is part of the content that won't be on the exam, but there's a lot of good key ideas here that they could recycle into the new exam this year. Okay? If you have any questions, let me know.